Welcome to step number 2 of Enable Training and Consulting's 7 Steps to FRC Robot Success videos. Let's jump right in by opening up the robot main block diagram. This is the stock code that is provided by National Instruments. In this video, we're going to modify the code so that it will stop the operation of the drive motors when a button on the joystick is pressed. With our first look at the code, we notice that there is a robot mode sub-VI, which is wired to the case selector of the main case structure. This indicates the state of the robot is dependent on the output of this sub-VI. Before moving on, make sure that the case structure is set to the teleop-enabled case. As we can see, there's a sub-VI in that case called teleop. Double-click on this icon to open the sub-VI, then press Ctrl-E to switch to the block diagram. Let's take a moment to understand exactly what this sub-VI is doing. This sub-VI executes every time the robot main while loop executes. That means that this code will run over and over again as long as the robot remains enabled in teleop mode. Let's open the Context Help menu by pressing Ctrl-H. Here we can see a string constant, left and right motors, wired into a sub-VI called drive ref num registry get. This sub-VI will recall the robot drive device reference that was stored in the registry in the begin sub-VI. If we float over the robot drive dev ref wire coming out of this sub-VI, we can see that it contains a very large amount of information. We don't need to worry about the specifics. We just need to make sure that this wire is connected to the arcade drive sub-VI, which needs this reference data to make the motors run. Below the drive sub-VIs, we can see another sub-VI getting the joystick reference. Just like with the motors, we have a string constant that names the joystick's registered reference. This enables the WPI joystick ref num registry get VI to get the reference that was created in the begin VI. This reference is wired into another sub-VI called joystick get. Joystick get extracts data from the joystick and puts it into a form that we can use. In this specific case, it gets data regarding the operational state and position of the joystick's axes and buttons. Right now, this code is simply extracting the data from the joystick axes and sending it to the sub-VI that makes the motors run whenever the joystick is not in the center or zero position. We want to change this code so that when a button on the joystick is pressed, the motors will not move regardless of the joystick position. We'll start by deleting the existing wires between the axes and the drive function. The Ctrl-B keyboard shortcut can be used to delete all of the resulting broken wires at once. Because we'll have two operational states, one when the button is pressed and one when it isn't, we'll use a case structure. Under Structures on the Functions palette, we'll select Case Structure and place it on the block diagram. Joystick button state data is already being acquired by the joystick get VI. We just need to extract that data. In order to extract this information, we must first unbundle it. So under Cluster Class and Variant in the Programming subpalette, we'll select the Unbundle by Name function and insert it below the axes information. Now we'll wire it up to the output of the joystick get sub-VI that gives the button data. As can be seen, the information is immediately displayed in our Unbundle function. One thing to note is that by clicking and dragging to expand the box, we can view all of the information that the incoming cluster has to offer. In this case, we only need the information from button number 1. Think back to what we want our code to do. As can be seen by its green color, the button data is a Boolean value of either true or false. Because our code is going to be dependent on the Boolean value of the button, we'll wire it into the selector terminal of our case structure. Now we can see that our case structure has two cases by default, one for true and one for false. Code inside the false case will be executed when the button has not been pressed. So what we're going to do is take our data from the X and Y axes and wire them straight through the false case and into the arcade drive function. When the button is not pressed, the joystick axes will still move the drive motors. Now we'll select the true case in our case structure. When the button is pressed, we want the drive to stop. So what we'll do is set a numeric constant of 0 inside the true case. Under numeric on the functions palette, we'll drag the constant into our case structure. It's set to 0 by default, so we do not need to modify its value. If we look at the wires going from the case structure tunnels to the arcade drive sub-VI, we'll notice that they're orange. This indicates that the wires are meant to carry double precision data. However, our numeric constant is blue, indicating that it's an integer data type. To change this, we'll right-click on the constant, and under Representation, we'll select Double Precision. Now our data types will match. Now we'll make sure our 0 constant is wired up to both the X and Y axes. The wires and tunnels should both be solid orange. We have now successfully added a button control to shut off the motors. Whenever the button is pressed, the code in our true case will execute, and a value of 0 will be passed to the arcade drive sub-VI. In step 2 of our 7 steps to FRC robot success, we modified the default LabVIEW FRC project by adding a button to act as a brake for our drive motors.